Welcome to an exploration of one of the most fascinating materials in your kitchen, mayonnaise, a metastable glass made of oil droplets. This is mayonnaise at the microscopic level. Billions of tiny oil droplets suspended in water, each one jammed against its neighbors like a crowded stadium. Let's start by understanding what an emulsion actually is and why mayonnaise is special. An emulsion is a mixture of two liquids that normally don't mix, like oil and water. Normally, oil and water separate immediately because water molecules are polar and oil molecules are nonpolar. Mayonnaise is an oil-in-water emulsion containing 70 to 80% oil by volume, which is an incredibly high concentration. Lecithin from egg yolk acts as an emulsifier, coating each oil droplet and preventing them from merging back together. Here's a single oil droplet coated with lecithin molecules. The lecithin forms a protective shell around each droplet. Now let's explore the critical concept of volume fraction, and what happens when droplets get too crowded. The volume, fraction phi, equals the volume of oil divided by the total volume of the mixture. For mayonnaise, phi is typically 0.7 to 0.8, meaning 70 to 80% of the total volume is oil droplets. Here's a critical question. What happens as the volume fraction increases and droplets get more crowded? At low volume fractions, around 0.3 or 0.4, droplets can move freely past each other like people in an empty room. But at high volume fractions above 0.64, droplets become jammed against each other like people in a packed subway car. They can't move without their neighbors moving too. The critical jamming transition occurs at phi critical approximately 0.64 for random sphere packing. Above this critical volume fraction, the system undergoes a jamming transition and becomes solid-like, even though it's made entirely of liquids. Mayonnaise behaves like a glass, but what does that actually mean? In normal glass, like window glass, atoms are frozen in a disordered, liquid-like arrangement instead of forming crystals. In a crystal, particles arrange in perfect periodic order like soldiers in formation. But in a glass, particles are frozen in a disordered, random arrangement like a snapshot of a liquid. Mayonnaise is exactly analogous. Oil droplets are frozen in a disordered, jammed state instead of separating into layers. While normal glasses have a glass transition temperature Tg, mayonnaise has a glass transition volume fraction phi c. Both are metastable states. They're stable for practical timescales but not true thermodynamic equilibrium. Eventually, over years, mayonnaise would separate. Now let's explore the fascinating flow behavior of mayonnaise through rheology, the science of deformation and flow. Here's a puzzling question. Why does mayonnaise sit like a solid dollop on your plate, but flow smoothly when you squeeze the bottle? The answer involves shear stress tau, which is the force per unit area applied tangentially to the material, and shear rate gamma dot, which measures how fast we're deforming the material. When we apply shear forces to mayonnaise, the top and bottom surfaces move in opposite directions, creating internal deformation. Mayonnaise is classified as a yield stress fluid, which means it requires a minimum stress to start flowing. The yield stress of typical mayonnaise is approximately 100 pascals, though this varies with formulation. Below the yield stress, mayonnaise acts like an elastic solid, maintaining its shape like jello. Above the yield stress, it flows like a thick liquid, which is why it comes out of the squeeze bottle. The yield stress is the answer to our question. It stays solid on your plate because gravity provides less than 100 pascals of stress, but squeezing provides much more. Mayonnaise exhibits another fascinating property called shear thinning, or pseudoplasticity. Viscosity eta equals shear stress divided by shear rate. This measures resistance to flow. For comparison, water has a viscosity of about 0.001 pascal seconds at room temperature. Mayonnaise at rest has a viscosity of 5 to 50 pascal seconds, making it 5,000 to 50,000 times more viscous than water. This graph shows shear thinning. As shear rate increases, viscosity decreases dramatically. The faster you stir, the thinner it gets. The mechanism is that jammed droplets get aligned and start sliding past each other in layers when you apply high shear. Under shear, droplets arrange into flowing layers, dramatically reducing resistance compared to their random jammed state. We can describe mayonnaise flow mathematically using the Herschel-Bulkley model. The Herschel-Bulkley equation states that total shear stress equals yield stress plus K times shear rate to the power n. Tau E is the yield stress we discussed, approximately 100 pascals for mayonnaise. K is the consistency index, roughly 10 pascal seconds to the n for typical mayonnaise. The flow index n is between 0.3 and 0.5 for mayonnaise. When n is less than 1, we have shear thinning behavior. Let's do a practical calculation. What stress is needed to spread mayonnaise with a knife? If we spread at 0.1 meters per second over a thickness of 1 millimeter, the shear rate is about 100 per second. Using our equation with n equals 0.4, we get tau equals 100 plus 63, approximately 163 pascals total. This corresponds to moderate resistance, which matches our everyday experience of spreading mayonnaise. Let's dive deeper into the theoretical framework that explains mayonnaise as a colloidal glass. A colloid contains particles sized from 1 nanometer to 1 micrometer suspended in another medium. Mayonnaise oil droplets have diameters of approximately 1 to 10 micrometers, making them colloidal particles. The Peclet number Pe equals 6 pi times solvent viscosity times droplet radius times velocity divided by kBt. The Peclet number compares convective transport from flow to diffusive transport from Brownian motion. For mayonnaise sitting still, P is much less than 1, meaning thermal diffusion dominates and droplets jiggle randomly. Under shear stress, P becomes much greater than 1, and flow dominates over thermal motion. The characteristic stress scale is approximately kBt divided by droplet radius cubed. For a 5 micrometer droplet at room temperature, this gives about 0.0001 pascals, much smaller than our yield stress. This huge difference confirms that mechanical jamming, not thermal fluctuations, controls mayonnaise behavior at room temperature. Let's understand why mayonnaise is metastable rather than truly stable. Here's a fundamental question. What is the true thermodynamic equilibrium state of oil and water? Answer: complete phase separation with oil floating on top of water, minimizing interfacial area and surface energy. The free energy cost equals surface tension gamma times interfacial area A. The oil-water interfacial tension is approximately 0.02 newtons per meter. An emulsion has enormous interfacial area between billions of droplets, making it very high in energy compared to separated phases. So why doesn't mayonnaise separate immediately into oil and water layers? The answer is kinetic barriers. The jammed state and lecithin coating create huge energy barriers that prevent droplets from merging. This energy diagram shows mayonnaise trapped in a local minimum, separated from the true minimum by a huge activation barrier. The typical lifetime of mayonnaise is months to years at room temperature before significant phase separation occurs. Now let's explore the remarkable phenomenon of shear melting in mayonnaise. Just as regular glass can soften and flow at high temperatures, mayonnaise undergoes a glass transition under mechanical stress. At rest, droplets are jammed in a disordered, solid-like state, unable to rearrange. Under shear, droplets unjam and flow in coordinated layers, transforming into a liquid-like state. We can think of shear reducing the effective volume fraction below the critical jamming point. Shear stress effectively creates free volume and pathways for droplets to slide past each other. Remarkably, this process is reversible. Remove the shear stress, and the droplets rejam into a solid state within seconds. This time-dependent recovery of viscosity after shear is called viscoelasticity. The recovery time is inversely related to the previous shear rate. Higher shear takes longer to recover. Let's ground our understanding with concrete numerical examples from everyday life. When you squeeze mayonnaise from a bottle, you're applying a shear rate of roughly 100 per second. Spreading with a knife generates about 50 per second shear rate. Industrial mixing during production uses shear rates up to 1,000 per second. The force needed equals shear stress times contact area. Let's calculate the force needed to spread mayonnaise over 10 square centimeters. At 163 pascals over 0.001 square meters, we need 0.163 newtons of force. This is equivalent to the weight of about 16 grams, roughly the weight of 3 nickels. Let's estimate the energy needed to mix 1 liter of mayonnaise at high shear for 1 minute. Energy equals stress times shear rate times volume times time. This gives approximately 12,000 joules, or about 3 food calories of energy. What happens when mayonnaise breaks, and why does it happen? Have you ever had mayonnaise separate into an oily mess? Let's understand why this happens. The primary failure mechanism is coalescence, where oil droplets merge together. 2 droplets approaching each other under thermal fluctuations or mechanical disturbance. When lecithin coating fails, they merge into one larger droplet, reducing the number of droplets and breaking the jammed network. Breaking occurs from too much oil overwhelming the emulsifier, insufficient lecithin, or excessive shear that ruptures the protective coating. Higher temperatures increase coalescence rates by making droplets more mobile and weakening lecithin layers. The time to breaking follows an Arrhenius relationship with activation energy EA. So mayonnaise breaks when the jammed droplet network collapses due to coalescence, temperature, or compositional imbalance. Mayonnaise shares fascinating similarities with other jammed and glassy systems. Foams like shaving cream are gas bubbles jammed in liquid, showing similar yield stress behavior. Pastes like toothpaste and gels are also jammed systems with yield stresses. Even sand piles are a type of granular glass at effectively zero temperature, jammed by friction. All these materials share the common feature of yield stress. They're solid below a critical stress and flow above it. Near the jamming transition, these systems show universal scaling behavior, where stress scales as phi minus phi c to some power alpha. The exponent alpha is typically between 1 and 2 for most jammed systems, reflecting universal physics. Understanding mayonnaise as a metastable glass has important applications in modern research and industry. Pharmaceutical researchers use jammed emulsions for controlled drug delivery, where medicines release as the emulsion unjams. Three-dimensional printing of soft materials relies on yield stress fluids that can hold shape until needed. Food scientists engineer textures by controlling volume fraction and particle interactions in emulsions and suspensions. Oil industry researchers study jamming phenomena to understand how oil flows through porous rock. This understanding has far-reaching implications across various fields, where materials flow behavior is crucial.